Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to look at solutions to homogeneous systems of linear equations. So, in this topic, we will review the definition of a homogeneous system of linear equations. We will compare solutions to non-homogeneous and the corresponding homogeneous systems of linear equations. We will see that the zero vector is always a solution to a homogeneous system of linear equations, and we're actually going to look at a number of results concerning all solutions to a homogeneous system of linear equations, and we will link these to other non-homogeneous systems of linear equations. Recall that a linear equation is said to be homogeneous if the right-hand side, or the constant, is zero. The term homogeneous implies that all the terms are of the same format. So in a homogeneous linear equation, all the terms are of the form a coefficient times an unknown. There is no constant term. A system of homogeneous linear equations is equivalent to asking if a linear combination of vectors equals the target zero vector. Now, given a system of homogeneous linear equations, we will call it a homogeneous system of linear equations. Also, given a system of linear equations, the corresponding homogeneous system is that system of linear equations where all the equations are equated to zero. So, for example, here we see a system of three linear equations in three unknowns. It happens that the second equation is homogeneous. The corresponding homogeneous system is this homogeneous system of linear equations where each of the three equations is equated to zero. Now, important. One equation within a system being homogeneous does not make the entire system homogeneous. If even one of the linear equations is not homogeneous, then the corresponding system is not homogeneous. Now, a non-homogeneous system of linear equations is any system where at least one linear equation is not homogeneous. Now, this corresponds to the question of finding a linear combination of vectors equaling a non-zero target vector. So, if any one entry in the target vector is not zero, the corresponding system of linear equations is also not a homogeneous system, or it is a non-homogeneous system. Now, recall that for a general system of linear equations, that is one which may or may not be homogeneous, you understand that there may be either no solutions, one unique solution, or infinitely many solutions, the third being the case if there is one or more free variables. For a homogeneous system of linear equations, however, we are always guaranteed that there is at least one solution. That solution is when all unknowns are assigned zero. So, for example, given this homogeneous linear equation, that equation is satisfied when all of the unknowns are assigned the value 0. Similarly, if we are trying to find a linear combination of the vectors u1 through un that equals a target vector being the 0 vector, you will see that this is satisfied also if all of the coefficients are equal to 0. Of course, this doesn't mean there is not more than one solution, but we are guaranteed that there is always one solution. Now, of course, there may be more than one solution to a homogeneous system of linear equations. For example, if I have the single equation shown here, then it does have infinitely many solutions, specifically all scalar multiples of the vector -1.51. Of course, if x2 is equal to 0, then so is x1. We call the solution when all unknowns are 0 to be the trivial solution. The trivial solution is always a solution to a homogeneous system of linear equations, and never is it a solution to a non-homogeneous system of linear equations. Thus, for a homogeneous system of linear equations, there may be either one unique solution, that is, the trivial solution, or infinitely many solutions, one of which, again, is the trivial solution. Now, recall from Gaussian elimination, all we did was add multiples of one row onto another. Consequently, if one column, in this case the target vector, or the last column, is all zeros, there is no operation in Gaussian elimination that will ever allow a non-zero entry to appear in the rightmost column. Consequently, if the target vector is the zero vector, then the rank of the matrix A will be the rank of the augmented matrix A with the target vector 0 for any matrix A. So consequently, it can never happen under any circumstances that there are no solutions. Now, recall that previously we found that for this non-homogeneous system of linear equations that it had one unique solution shown here. If you were to solve the corresponding homogeneous system of linear equations, you would find that there is only one solution as well, and that is the trivial solution. Previously, we found that this system of linear equations had one free variable and therefore infinitely many solutions. If you were to return to this problem and solve the corresponding homogeneous system of linear equations, you would note that the solution is similar. However, the constant vector is now gone. Now it is simply all scalar multiples of the vector -1.410. Now, previously we found that this system of linear equations had no solutions. If you were to solve the corresponding homogeneous system of linear equations, however, you would find that there are infinitely many solutions, specifically all scalar multiples of the vector 22, 3, 15. Previously, we found that this system of linear equations had infinitely many solutions, as shown here. Well, if you were to solve the corresponding homogeneous system of linear equations, you would note that the solution is essentially the same, except once again, the constant vector in the solution is now 0. The solution to the homogeneous system is simply all scalar multiples of the vector 1, 0, 0. Recall that previously we found that the solution to this system of linear equations has one unique solution shown here. If you were to solve the corresponding homogeneous system of linear equations, you would find that yes, there is one unique solution, but in this case, it is now the trivial solution. When we previously solved this system, we found that there were infinitely many solutions, specifically a constant vector plus all linear combinations of 3 specific vectors. Well, here is the solution to the corresponding homogeneous system. As you will note, the solution looks eerily familiar. It is, in fact, the previous solution with the constant vector eliminated, essentially set to 0. So now the solution to the corresponding homogeneous system is all linear combinations of 3 vectors. You will recall that all linear combinations of 3 vectors forms something else, specifically perhaps a subspace? Now, previously we found that the solution to this system of linear equations had one unique solution. As you may guess, the corresponding homogeneous system of linear equations also has only one unique solution, only now it is the trivial solution. Now, the trivial solution is the 0 vector. You may recall also that the 0 vector is a subspace of any vector space. It is the subspace containing only the 0 vector. Thus, we may note that given a non-homogeneous system of linear equations, if the corresponding homogeneous system of linear equations has only the trivial solution, then the non-homogeneous system either has a unique non-zero solution or it has no solutions at all. If the corresponding homogeneous system of equations has infinitely many solutions, then the non-homogeneous system either also has infinitely many solutions, but the 0 vector is not in that collection, or it still may have no solutions. Theorem 1. If x is a solution to a system of linear equations, and x naught is a solution to the corresponding homogeneous system, then x plus all scalar multiples of x naught are also all solutions to the system of linear equations. So, to solve this, we're going to use the linear combination of vectors equaling a target vector format of a system of linear equations. So, let us suppose we are finding a linear combination of the vectors u1 through un that equals the target vector v. Well, if x is a solution to this, then if we substitute x1 through xn into this equation, we get v. And if x naught is a solution to the corresponding homogeneous system, then if we substitute the entries of the vector x naught into this equation, that must equal the target vector, the 0 vector. All right, so both of these must be true. Now, if you were to now add the first entry of the vector x plus alpha times the first entry of the vector x naught, and so on and so forth for every single entry, then we get the vector x plus alpha times x naught. However, let's see what happens. Now this new vector, if we substitute its entries into the linear combination, we get the following. Now, fortunately, all of you know the properties of vector and vector addition and scalar multiplication. So knowing this, you could expand this and then collect the appropriate terms to see that this is nothing more than the sum on the left plus alpha times the sum on the right. But the sum on the left, or the linear combination on the left, equals v, and the linear combination on the right equals the 0 vector. So we essentially have v plus a scalar multiple of the 0 vector, which is, of course, v. Thus, x plus all scalar multiples of any solution to the corresponding homogeneous system is also a solution to the original system of linear equations. Straightforward enough. Now, this does not necessarily imply that every solution or every system of linear equations has infinitely many solutions. For if the corresponding homogeneous system has only the zero vector as a solution, then x plus any scalar multiple of the zero vector is still x. For example, this vector x, 907, is a solution to this non-homogeneous system of linear equations. Also, this vector x naught is a solution to the corresponding homogeneous system of linear equations. Consequently, the first vector plus all scalar multiples of the second vector are all solutions to the original non-homogeneous system of linear equations. This may or may not be all of them, but it is certainly a start. And if you take a look at the matrix, you should realize that, yeah, there's probably going to be one free variable. So in other words, this should actually represent all solutions to the original system of linear equations. Theorem. A system of linear equations has a unique solution only if the corresponding homogeneous system has only the trivial solution. All right, suppose our system of linear equations has two solutions. So alpha 1 through alpha n are the coefficients that allow the first linear combination of the vectors u1 through un to equal the target vector, and also beta 1 through beta n are the coefficients on the right-hand side that allow the left-hand linear combination of vectors u1 through un to equal the target vector v. Let us consider the vector of alpha 1 through alpha n minus the vector of the values beta 1 through beta n. This is an n-dimensional vector. Now, let's see what happens if we take the following linear combination of the vectors u1 through un. Well, using the properties of scalar multiplication and vector addition, which you know, you can rewrite this linear combination of the vectors u1 through un as this difference of two linear combinations. The thing is that the first equals v, as does the second. So this is actually equal to v minus v, which is the zero vector. What this says, therefore, is that if you have the coefficients alpha 1 minus beta 1, alpha 2 minus beta 2, and so on and so forth up until alpha n minus beta n, then those solutions, those are a solution to the homogeneous system of linear equations. All right, so if the vector alpha minus beta is a solution to the homogeneous system, and the homogeneous system only has the trivial solution, then alpha minus beta must be equal to the zero vector. So therefore, if we had two solutions, those solutions must be equal. Therefore, if the corresponding homogeneous system has only the trivial solution, then the system of linear equations, if it has a solution, must have a unique solution. Theorem. All solutions to a homogeneous system of linear equations always forms a subspace of f to the n, where f can either be the reals or the complex numbers. Proof. Suppose we have two solutions, the vector alpha with entries alpha 1 through alpha n, and the vector beta with entries beta 1 through beta n. Well, let us take the first one, the vector alpha, and multiply it by gamma. Well, if we multiply the vector alpha by gamma, that multiplies each of the entries of the vector alpha by gamma. Therefore, let us see what happens if we take the linear combination of the vectors u1 through un with the coefficients gamma times alpha 1, gamma times alpha 2, and so on and so forth. Well, using the properties of vector addition and scalar multiplication, you will find that you can factor out the gamma from the linear combination. So, therefore, all we're left with is gamma with a linear combination that we know equals the vector, the zero vector. So this just ends up being gamma times the zero vector, and any scalar times the zero vector is the zero vector. Thus, gamma times the vector alpha is still a solution to the homogeneous system of linear equations. Similarly, if we were to add the two solutions, we would get an n-dimensional vector with entries alpha 1 plus beta 1, alpha 2 plus beta 2, and so on and so forth. And if we take this linear combination of the vectors u, we can determine once again that using the properties of scalar multiplication and vector addition, that the first sum is equal to this sum of two linear combinations. But each of these linear combinations is already a solution to the homogeneous system, so both of those are equal to 0, and 0 plus 0 is equal to the zero vector, and therefore the sum of any two vectors that are solutions to a homogeneous system of linear equations is also a solution to that homogeneous system of linear equations. Therefore, given any vector that is a solution, all scalar multiples of that vector are also solutions, and given two vectors that are solutions, the sum of those two vectors is also a solution. Therefore, the collection of all solutions to a homogeneous system of linear equations must form a subspace. Theorem: the collection of all solutions to a non-homogeneous system of linear equations is never a subspace of f to the n, where f is either the reals or the complex numbers. Proof. Well, if the system is not homogeneous, then the trivial solution, that is the n-dimensional zero vector, cannot be a solution. Therefore, the zero vector is not in the collection of all solutions. If the zero vector is not in the collection of all solutions, that collection cannot be a subspace, because every subspace must contain the zero vector. Now, because the solution to a homogeneous system of linear equations is always a subspace of f to the n, we can always write the collection of all solutions as the span of a set of vectors. So, for example, all solutions to this system of 3 linear equations in 5 unknowns, which is homogeneous, has the following general solution. This general solution is the span of the 3 given vectors. Here's a nice little result that you will actually use in your second year calculus course. Suppose you have found one particular solution to a non-homogeneous system of linear equations. Suppose also that you know all solutions to the corresponding homogeneous system. Well, if you add that particular solution to each solution of the corresponding homogeneous system, you get all solutions to the non-homogeneous system of linear equations. This is a nice result. For example, here we see a non-homogeneous system of 3 linear equations in 5 unknowns. One solution to this system is the vector 1, 0, 2, 0, 0. However, there are more solutions. After all, there must be at least 2 free variables. Well, in a previous slide, we saw that all solutions to the corresponding homogeneous system could be described by the span of these 3 vectors. Consequently, what that means is that if we add the vector x to any solution in that span, we get a solution to the non-homogeneous system of linear equations. Non-homogeneous system of linear equations. So, if we just add 1, 0, 2, 0, 0 onto any linear combination of these 3 vectors, we are guaranteed that we get another solution to this non-homogeneous system of linear equations. So here are some nice results we've seen so far that may be useful to remember. If x1 and x2 are solutions to a homogeneous system of linear equations, then so is any linear combination of the vectors x1 and x2. If x1 and x2 are solutions to a non-homogeneous system of linear equations, then neither x1 plus x2 nor alpha times x1 for any alpha not equal to 1 are solutions to that non-homogeneous system. If x1 and x2 are solutions to a non-homogeneous system of linear equations, then x1 minus x2 is a solution to the corresponding homogeneous system. Also, if x1 and x2 are solutions to a non-homogeneous system of linear equations, then alpha times x1 plus 1 minus alpha times x2 is also a solution to that non-homogeneous system of linear equations for all scalar values of alpha. So, following this topic, you now understand what a homogeneous system of linear equations is. You also know that the zero vector is a solution to a homogeneous system. In fact, all solutions to a homogeneous system of linear equations is a subspace of r to the n. You also know that all solutions to a non-homogeneous system of linear equations is never a subspace and never includes the zero vector. You understand that there is an interesting and strong relationship between the solutions to a non-homogeneous system of linear equations and the corresponding homogeneous system. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!